Hello, hello. All right, looks like we're streaming. Gonna sit in the Discord for a bit and see if anybody's gonna turn up. Hello? Not sure if anybody's even watching right now. Let's check the live stream. Hello? Not sure if anybody's even watching right now. Let's check the... Yes, I'm working. Close that. All right, I'm going to sit in Discord for a bit. If anybody's watching and hearing me, join the voice channel, the general chat. Hey, Ram, do you have a mic? Ram, do you have a mic? I want to see if you can engage. Can you say something if you have a mic? I think I'm going to give it like another minute or so, then I'm going to go ahead and start. If you're watching this, after I streamed it, I'll go ahead and just timestamp it for when I actually start lecturing. So far I have one person in here. Yep, so sorry, if you have any kind of ambient noise, I have people at the house, and we're all working at home right now, right? So I requested they be quiet, but you never know when you're at home. All right, I will be right back. Yeah, I'm going to lecture for about 80 minutes today. I know they can hear me right now, so no, too. Oh, okay. Yeah, I'm going to cover all of Chapter 7 today, or at least the remainder of it. I feel like I'm game streaming here, man. Except it's gonna be like nerdy chemistry stuff. Let's do it. Gotta go viral with the Gen Chem over here. All right, guys. I think I'm gonna go ahead and get started. I'm not sure if anybody else is gonna show up. I would really like for you guys do, because it'll allow you to engage with lecture. Ask questions, that kind of thing, and it definitely could be a better experience overall if you guys are actually able to be here when I'm actually streaming. So to say you don't have to be, so I'm not going to mark you guys off or anything if you're not going to be able to make it to these, because I understand that people's home lives are crazy right now. So perfectly understandable, but hopefully you guys catch them at least some point within the time frame that I actually broadcast these. So I'm going to go ahead and just switch over to the I was going to say that we might have a few interruptions. This is how you go viral, right? You show a cat. So this is Chloe. She will probably be interrupting me often. Just can't help it. All right. So I have a PowerPoint here, and you guys should be, you should have this, up in Canvas. And let me adjust this stuff, and we'll start talking. All right. And part of me, I'm still kind of a noob at some of this stuff, so I think I'm figuring it out, though. All right. So last time we talked about chemical reactions and how to balance them. Kind of did a general introduction on the different types. So I wanted to do a little bit of a recap we did last time, do a few practice, and then as I mentioned last time in class, we were going to kind of deep dive into a lot of this content today. So looks like on slide 110, we did talk about different reaction types. I don't tend to follow these in the exact order they go, so I will be jumping around a little bit. Slide 110, I believe, had the reactions. There they go. All right, so just to recap, we had the different types of reactions. These are the generic categories, and then you're going to be responsible for these specific categories. So in general, we have the synthesis reactions where two small things become one large thing. We then have the decomposition reactions where you have something small or something large breaking apart into smaller components. That's decomposition. And then we also have the single displacement and the double displacement, and I described it as sort of like a partner swap, where typically they involve ions, and they will just trade partners essentially. So I just want to go ahead and start off by just kind of looking. There is a slide in here for the methane example we did. Actually getting a little bit ahead of myself. I did want to talk a little bit about the symbols. Wasn't sure if I was too clear on these last time, but let's go ahead, I think it was slide 17. Yep, so here we go. So we have the different symbols that we like to use when talking about different states that these different reagents are in, the reactants and products. We like to use the letter G for gas, L for liquid, S for solid. And then we're going to go quite a bit into what the AQ symbol means today. That means that this compound is aqueous, meaning it is dissolved in water. In general, if the compound is saying it's aqueous and it's ionic, typically that means that it's broken apart into its cation and anions. And in the case where it's molecular, typically those are all they're still intact and they don't actually ionize, break apart in water. We do have some other things here that are typically often written on reaction arrows, and these kind of help give the reader a little bit more information on what exact kind of conditions you might need. The most common one is that little triangle symbol for heat. I will tend to use that a lot. And then we have HNu, that is for light, or seeing as HV, but we actually say HNu. And I will use that a lot more in organic chemistry than this course. And then we have the other ones for mechanical and electrical that you might see on the arrows. Oops. All right, so let's go ahead and just back up a little bit, take a look at that methane reaction again. We did do this in class. This should already be in your lecture notes. So in general, we have a combustion reaction, and then when you have a hydrocarbon and oxygen, you typically will get carbon dioxide and gaseous water. The reason why we get gaseous water instead of liquid water because these reactions generate a lot of energy, they give off a lot of heat, so it's enough to push the water into the gas phase. We also talked quite a bit of detail about when you write a reaction, we have to observe the conservation of mass. Meaning that matter cannot be created or destroyed. That essentially means in terms of balancing equation is that you have to have the equal number of atoms on both sides. And taking a look at methane again. So here we kind of have a visual what's happening here. So if you actually add up the atoms on both sides, they should be equal. So I just want to go ahead and switch over to my makeshift document camera and then work through two combustion problems, and then we'll kind of just go from there. So let me switch this up. Right, there we go. We probably don't need a periodic table too much today. It might be useful for charges, but if you don't have a periodic table with you, it's okay. I will have this one to reference. But in general, when studying chemistry, it's just good practice to have your periodic table handy. You never know when you might need it. All right, so recap here. Like I said, this should be in your notes. I just want to make sure we're getting plenty of practice. So combustion of methane, so methane is a CH4. And I also want to apologize about the lighting here. I'm actually going to set up in a different position next time I do this, because I forgot about the window that I have like right there that lets in light, and it's kind of on the second floor, so I can't actually reach it to cover it. So anyway, moving along here. So this is probably going to be a gas at room temperature. And then we have our oxygen, O2, likely a gas as well. So reactants, we're going to have products here, and under complete combustion conditions, typically meaning excess O2, we're going to have CO2 gas plus H2O gas. All right, so I like to make a little table of all the different atoms we have involved here. So we're going to have a C, H, and O. And when you're working with the combustion of hydrocarbons, I highly recommend that you balance them in this order. So once again, so it's methane. All right. So you always want to start off with the initial tally. So we go ahead and say we have 1 carbon, 4 hydrogens, 2 oxygens. Oops, let me adjust the face thing. I'm not blocking the view with my smiling face. Here we go. Right, and then so here on the reactant side we have this amount, and then on the product side we have 1, 2, and 3. It typically starts off that way. So then what you want to do here is we can go ahead and add coefficients in front of each of the species, but we cannot change subscripts. Remember that if you change the subscript, you change the identity of the compound. And I believe the example I mentioned was that, suppose you put an O3 here, that's no longer oxygen gas, that is now ozone. So it makes a difference. So starting off here, I see, okay, we're already okay on the carbons, and then on the hydrogens, looks like we need to double up on the water, so 2. And then we can retally here, so we now have 4. And then over here, we can go ahead and balance oxygens, but we have to retally those as well. So it looks like we have 2 and 2, so 4 total. And then we got to go back to this side. We can now balance the oxygens, and I just put a 2 in front of that one, and we are all good. So we did have some examples last time in class where, remember that if you ended up with an odd number at this point, after you balance this side, if you have an odd number here, you have to use a fraction to balance here. You just write how many you need over 2, and then to remove the fraction, you go ahead and multiply all the way through by 2. So if you multiply this one by 2 to get rid of the fraction, you have to do that to everybody in the reaction, just to make sure you're keeping your mass balance. All right, so let's go ahead and do another one. This one might be a little bit more challenging, and I want to talk about the combustion of ethanol. Sometimes there are not just C's and H's in there. So we have ethanol. This is the organic chemist to me drawing stuff out. But in this class, we're going to write this like C2H5OH. I'm going to start with the lighting here. The light is coming right in the window right here, and yeah, it's in my face. All right, so the rest of the reaction is the same. We have a little bit difference in the hydrocarbon. Just make sure we understand what I'm talking about here. This is ethanol. It's the alcohol people like to drink. And then we have oxygen is the same. Still need the oxygen for these to burn. And then the products are also the same. And just like before, under complete combustion conditions, you get these products. If it's oxygen starved, you get things like carbon monoxide and elemental carbon coming off instead. All right, so tallying up here, we have 2 carbons. So here, notice how I'm writing, I have an H here and an H here. You have to make sure you account for that. So we have 6 hydrogens total. And then looking at our oxygens here, just like we have it in multiple places, we need to account for that as well. So we have 3 over here. All right, and then this side starts out as 1, 2, and 3. All right, just go C, H, and then O. So I'm going to start off by going and balancing the carbon by putting a 2 in front of CO2. You now have 2 carbons. And then for the hydrogens, it looks like we need 3 waters instead of 1. So that gives us 6. And then at this point, we can retally the oxygens to see what we have. So we have 3 from the water, and then 4. 2 times 2 is 4, plus 3 is 7. All right, be careful here, because if you have a hydrocarbon that has oxygen in it also, you might not have to do the fraction trick that we were talking about last time. So notice here, if I put a 3 in front of the O2, that gives me 6 oxygens, and then I have the 1 from the ethanol, and that puts it at 7. So equal both sides, work deal with mass balance. We are done with this problem. All right. And let me check the Discord. There is still one person in the Discord. Looks like I'm seeing other people are online. If you're hearing me, please in Discord join the general voice channel if you want to ask questions. It'll make this a lot more engaging if you guys do this. I am not checking any comments on YouTube right now. I'll check the comments after the stream. All right, so let's go ahead and take a look at some other reactions. Let's go ahead and take a look at a redox reaction. Oh, something happened weird. I'm getting some kind of weird feedback right now. I think I'm hearing someone's mic. Yeah, Kendall, please. Yeah. Oh, I see you muted yourself. Thank you. Yeah, so if you're unable to figure out how the push to talk works, you can go ahead and just mute yourself, and then if you want to talk, just unmute yourself, and that'll work too. But let me just show you guys real quick, just to make sure everybody's understanding how this works. So, let me turn the desk capture on. There we go. And then over here in Discord, it's actually, let me full screen this. Yeah, it's similar on the phone app too, but wherever your little logo is, your name, there's a little cogwheel. It's right here. I'm on a PC right now, but your phone might be just a little bit different. And then in the options, there's video and voice settings, or voice and video settings. And then in here, you can set your push-to-talk options. You can check if your mic is working, all that fun stuff. In the case you want to log out, this is actually where they kind of buried the log out thing. I recommend you do that when you're not actively using the app, because this app tends to spam. So either do that or turn off the notifications from this app if you're using it on your phone. All right, so let's go ahead and minimize the Discord. Hopefully you guys are understanding. You guys can always message me if you have any questions and need help getting it all set up. I'm here to help you guys. All right, so let's go ahead and switch back to the discussion. All right, turn the desk capture off. All right, so I said I wanted to do a redox problem, so let's go ahead and switch back over to this view. All right, so here I'm going to go ahead and take a iron. This is going to be solid, and then we're going to say plus nitric acid, HNO3. Hopefully I still remember your names. This one's going to be aqueous. And then what's going to end up happening here is we're going to end up with a single displacement reaction. Iron is going to replace hydrogen. And when we write out the formula here, we need to make sure that we're getting the correct formulas, like the right number of ions, right number of nitrates, that kind of thing. So I'm going to go ahead and just write it as FeNO3. I left myself a little bit of space just in case I need parentheses. I believe I will here. And it turns out in this particular example, iron will typically oxidize to a 3+, and we saw a few chapters ago that nitrates are -1. All right, and then I'm writing them in different colors above this because when you're actually writing out your reaction, we typically don't include those as part of our reaction. So what do you guys think? So how many nitrates should I have to balance this out? I wonder if anybody can hear me, can answer me on Discord. How many nitrates do we need to balance out this formula right here? Oops, bump the camera. It's all right. Anyway, it takes 3. Oops, messing up my view. It takes 3. And then the side product here will be H2, and this will be a gas. And then FeNO3, 3 will be aqueous as well. All right, so on this one here, we do have a polyatomic ion. In the case where you have a polyatomic ion, I recommend that you balance it as if the polyatomic ion was one element. And you can do that only if the polyatomic ion is unchanged from one side to the other. So here we have an NO3, and then it's still NO3. We're going to have to balance the number of them, but their identity is the same. So when I write out what I need to balance, I'm going to go ahead and say Fe, H, and then NO3, and I'm going to treat this as if it were an element. Oops, wrote that a little bit off the page there. There we go. All right, so tally up. So we have 1, and then 1 on this side for everything. And then on this side we have 1 iron, 2 hydrogens, and 3 nitrates. All right, so then what we need to do, it looks like I like to balance from heaviest first and then just go down. So I'm going to go ahead and balance the hydrogens by putting a 2 over here, like so. So then retally like this. All right, so how do we balance this out here? So it looks like we have 3 nitrates here. In this kind of situation, I don't think it's going to balance too nicely, with just like one more coefficient. So it looks like we're going to probably have to do some kind of common multiple thing here. So here we're going to have 3 nitrates as part of this formula. And I think we can probably get it to work out if I put a 2 here, and then that'll give me 6 nitrates. So I'm going to do a little bit of back and forth on these to get them to work out. So 6 nitrates, and then my iron count's now 2. I'm going to drop a 2 in front of iron to adjust for that change that we made. We're probably going to have to change that coefficient. I believe now we can change it to a 6. Let's go ahead and erase that. So go ahead and put a 6 there. And then we can get our hydrogen count correct. So now we have 6 hydrogens. And then we can put a 3 in front of the H2. Yeah, so general rules that I like to follow. So you go from like heavy lone elements first and leave diatomics for last, because they tend to be the last thing that ends up happening in the way they work out typically, at least in my experience. So I believe we are now all balanced. We now have 6 nitrates also. All right, so let's talk a little bit about redox. But before I go into that, we should be able to identify what kind of generic reaction this is. Because we have the single partner swap, Fe for H, this is a single displacement. So single displacement. All right. So when talking about redox reactions, typically the kind of thing that we look at here is if things are changing charges from one side to the other. So I'm going to go ahead and fill in the rest of the charges of everything in here, and then we can see if things are changing or not, and they definitely are. So if something is elemental, the charge is 0 by definition. So typically if we write them that way, you're not putting a charge on them. It is implied that the charge is 0. They have equal protons and electrons, no charges. So if you look at iron from one side to the other, the charge went from a 0 to a 3+. And then over here, we're seeing that hydrogen is typically a +1 when it's part of compounds. There are some exceptions to that, but for most part of this class, they're going to typically be +1. And then hydrogen is a diatomic element, meaning that if it has that elemental form, it has a charge of 0. So then we can also see here that the charge on hydrogen has changed from the reactants to the products. Went from a +1 to a 0. All right, so in general, what we like to say is that if something lost electrons, it's oxidized. So let me go ahead and take a look here. We had a slide for this that I wanted to reference, slide number 98, I believe I tagged here. And then I'll pull it up here. All right, and then let me switch this thing. All right. So typically when you have a redox reaction, you have what's called a oxidation and reduction happening at the same time. In general, we like to say that if something lost electrons, it was oxidized, and then if it gained electrons, it was reduction. A little bit of a word salad here on this slide. Let me just work on the dot cam. That's probably what I would have did in lecture anyway. So, and then hang on to this. Let's come back to that reaction after I give you some definitions here. So we say it's an oxidation. This is when something lost electrons. And then we have the other case where it's a reduction. This is the case where it gained electrons. And these always happen in tandem, meaning they happen at the same time. You typically don't have one without the other. And that's where the term redox comes from. They're kind of just smashing these two words together into one. So redox. There are a couple different ways to remember this. You can kind of logic your way to remembering this, and there's also some acronyms that we can use to remember it too that are kind of silly, but they work. I still use actually one of them today. So if you think about it here, if you have an oxidation, does not necessarily mean it reacted with oxygen. It just means that it lost electrons. So if it lost electrons, kind of like which direction do you think the charge went, like up or down? So if something lost electrons, it means that it now has, you know, if you think about it, if it's a neutral element, if it lost electrons, that means it formed a cation, meaning it's positive. So typically what happens with an oxidation is the charge goes up. If you have a charge increase, typically that means you have an oxidation. And then if something gained electrons, so for example, if something had 18 electrons at the start, it gained 2 more, it's probably going to have a -2 charge. And then we see that the charge went downward. So I specifically focus on this word when remembering this. Reduction means reducing the charge, and so the charge went down. The really common phrase that people use for this to remember it is Leo says Ger. So what this stands for here is lose electrons, oxidation, and then we have gain electrons, reduction. So that in mind, let's go ahead and... Hi, Tristan.
Hi.
You want to say hi to my class? Hang on, guys. We got a visitor.
Hi.
Hi. You gonna give him a dab? Give him a dab. Do it. Dab time. Yay! Yay! What do you need, buddy? Told you guys might have interruptions. You want your tablet? Okay. All right, here you go. Sorry, guys. What happens when you have a 6-year-old around? He should be in kindergarten right now and not at home. But unfortunately, yeah, you guys know what's going on. So, oh, I messed up something. Hang on, let me fix my thing. I messed it up. Sorry, guys. All right, we were on presenter camera. There we go. All right, so we had this reaction back, and then let me just put the notes underneath it real quick, and then we can talk about it. So we had the redox reaction definitions there. There we go. So what I'm going to have you guys do is that, so basically after you have a reaction, you can take a look at what happened, and I'm going to have you guys identify exactly like which elements were oxidized, which ones were reduced. So taking a look at iron, so on here you want to focus on anything that's changing charges, and those are the ones that are reacting. So here we have the iron, and that's becoming 0 to +3. So I like to identify them by drawing little brackets between them, both different versions of it, like that, and seeing how the charge went upward. Looking at our definitions here, this is by definition an oxidation. So I like to write ox on there. And then taking a look at the other thing here, nitrate didn't change charges. It started at a -1, ended up at the -1. It's not actually part of the reaction. It's kind of just watching the reaction happen. We actually call them spectators, but I'm getting ahead of myself. But here, you go ahead and connect these guys, and we're seeing here the charge went downward. So this is a reduction. I like to write RED for reduction. So we have our redox. There we go. All right, if there's, all right. Any questions? Let's see if anybody wants to ask a question. Give it a second. Let it absorb a little bit. All right. So another thing that we're going to be doing here is after you guys have a balanced reaction, typically we can reduce them a little bit further to make them, just kind of clean them up a little bit, and you kind of focus in on exactly what's happening. And so what we have right now, this is called the molecular reaction here. It's the full reaction. We can do a few things here, but we'll actually save this reaction. I'll use this as an example after we get through the dissociation section. And then, but yeah, we'll definitely come back to this one. All right, what did I want to do next? Oh yeah, I wanted to switch over to talking about dissociation. So I have slide number 40 tagged for this topic. 40, There we go, aqueous solutions. All right, I'm actually showing it here. Oops, my desktop. Oh, come on, wrong one. Yeah, because bear with me, because I'm still learning this stuff. What's going on? Why they're not showing? Oh, come on. Technical difficulties. I'm trying to get. Oh, you guys are seeing it. My bad. Sorry, I'm still learning the software. So I want to go ahead and take a look at the aqueous solutions. So typically, what you have is things that are in solution. For saying they're aqueous and they're ionic, typically that means that they broke apart into their ions. And it's just collectively referred to as an aqueous solution. So let me switch over to the dock camera again and show you what I'm talking about. So typically if you have something like NaCl, this is definitely something that's going to be aqueous. This is how we write the formula, is NaClAq. And when you read that, what you want to think it is, it's essentially Na plus in solution, and then chloride in solution. This is what I mean by disassociating. They're breaking apart into their components. Water definitely does this to things that are soluble. So we have this. Oftentimes, when I write ions, it's kind of implied they're aqueous. So I will, oftentimes, for the sake of brevity, just kind of cut off that AQ symbol. But I'm hoping you guys know what I mean when I'm writing this out as simply Na plus and Cl minus. And then when you guys are doing this in your homework, you guys are writing them out that way, knowing that these are basically dissolved in solution. All right. Switch back over to all. All right. I wanted to talk a little bit more about this here. So we have some slides showing this here. You guys are seeing this? Yep, you are seeing this. Yep, so things are breaking up. They're together at first if they're solid, and then they break apart when they are in solution. So one thing you guys are going to have to figure out is taking a look at a different compound. You're going to have to be able to tell me whether or not you write the symbol AQ or you write the symbol S on it. And there are actually rules for this, and I just want to go ahead and take a look at these. These are on slides 50 and 51. So here are the solubility rules. Typically, assuming we were doing an in-class exam, I actually provide these charts for you guys on the exams. I typically put on the back side of the periodic table, because I generally I'm not a fan of people memorizing tables, and this is the table. Keep in mind, though, that it is very beneficial to remember parts of it, because certain ions are very, very common, and they will speed up the time it takes for you guys to do a problem, if you're not always having to look things up on a table. And I also want to point out here too that if you're taking Gen Chem, next semester, a lot of people don't actually provide these, and it all depends on what teacher you get. But I know a lot of people don't provide these for their students in 121, so just be aware of that. So the parts, the table we're looking at right now is for compounds that are generally soluble in water. In general, things that, I think I bumped my camera. Jeez, sorry. The things that are typically always soluble are your group 1 elements. We're taking a look at like lithium, sodium, potassium. Someone's phone's going off. All right. Also in the list of that category are the ammonium ions. Those are all cations. Notice they're cations. And then we have some general soluble anions, your nitrates, and acetates are always soluble. When you start looking at the exceptions is when things start getting tricky. So before we actually start doing actual reactions with solubility and precipitation reactions, we have to kind of go over solubility rules, so that if you see a compound, you can use this table to kind of recognize if something is soluble or not. All right. So for example, let's go ahead and switch over to the dot chem again. There we go. So if I had something like lithium and chloride, we have LiCl. And to specify to the reader that the soluble or not is based off what state you write after it. So if this compound is soluble, I write AQ. If it's insoluble, I write S. So you may notice from the table that I just showed you guys a second ago that lithium compounds are typically always soluble. So this is definitely going to be aqueous. So AQ. But for example, if chlorides are typically soluble, we have some exceptions though. Back on the table, silver typically precipitates out of halogens, and we see that in the exceptions. So looking at the exceptions, oops, there we go, that chlorides are typically soluble, that's why they're on this particular table, but we have some exceptions. So if it's paired with silver, you say that it's solid, insoluble. All right, so there's that table, and then let me quickly talk about the other table, then we're going to do a bunch of examples of predicting solubility. Oop, there we go. So the ones that are, oops, hang on, there we go. If I minimize on the desktop, it actually closes it out on the stream thing, so I got it figured out. All right, so these compounds are generally insoluble, meaning they have a solid after their formula. And then there are hydroxides, OH, sulfides, and then we have our carbonates and phosphates. Take a look at the exceptions there. So exceptions mean that if they're paired with these guys here, then that means that they're typically soluble. So you may notice there that the ones that are always soluble are the exceptions on this table. So that top row and all the exceptions are the same as the ones that are always soluble on the previous table. So I highly recommend you memorize at least those four because they're very common. Lithium, sodium, potassium is literally group 1. And then we have ammonium, which is kind of added to that group. It turns out, though, that for the exceptions here, that the group 2 elements, calcium, strontium, barium, the +2 charged ones, are exceptions. Meaning that those ones are going to be soluble in solution. And then we have the bottom row there, the phosphates and carbonates. The only exceptions are the ones that are always soluble. So that way the two tables are consistent with each other. They don't have conflicts in them. So let's switch over to the. Hopefully you guys have these tables available. We're on the internet right now, so you guys should be able to pull these off the modules in Canvas. And that was slide 51 that I'm on right now. All right, so with this in mind, let's go ahead and take a look at a couple of these ones. So what if I had something like magnesium hydroxide? So I could potentially give you the name here. We don't have the right formula right now. Magnesium is typically a +2. And it's different colors here. Magnesium is typically a +2. OH is a polyatomic ion. That was one of the ones you guys were supposed to memorize during the last test at the -1. So we need 2 of these in the formula. So here we go, like that. And then typically hydroxides are water insoluble, but we need to make sure we check to see if magnesium is an exception. So back over to the table. So taking a look at hydroxides, if you see magnesium as an exception in the table there, I'm seeing the group 1 elements, ammonium, and then calcium, strontium, barium. This is probably soluble, so I'm going to go ahead and write AQ on this. So AQ, like that. Next one here is take a look at N-sodium sulfide, so NaS. Same thing as last time, we don't have the right formula. Sulfides are typically a 2-, 1+ for sodiums, so it looks like we need 2 of these sulfides. I'm not using no parentheses here because sulfide is not polyatomic. And if you memorize which ones are always soluble, it's a really quick problem here. It's got sodium, AQ. You're done. All right, so pretty much anything that has sodium in them are going to be soluble. So we have sodium acetate I'm writing up now. Turns out that both of these ions are always soluble. They're both on the always soluble part of the table. Aqueous. So nacho is soluble. there was my chemistry pun of the day. Nachos are soluble. All right, let's go ahead and just do a couple more of these, then we'll go ahead and move on. So what if we have something like, let's do another sulfide one. What if we have magnesium sulfide, MgS? They're both at a +2. Sorry, +2, -2. We don't need any subscripts here because they're already working out balanced. So MgS is good. So sulfides are one of the ones that are typically insoluble. So we think, okay, it might be insoluble. Let's go ahead and check the list and see if we have magnesium as an exception. So let's switch back over. So the first one is for the ones that are, sorry, we're on the one right now. So typically insoluble. We have some exceptions here. Magnesium is not on the list here. So that means that, what? It's AQ, right? Is that right? Yeah, so the way we read this here is that if these are typically insoluble and have one of the exceptions, it's soluble. If your exception is not in that list there, then we go ahead and say solid for that. All right. So let's just go ahead and do a problem now. I think you guys kind of get the basic gist here. There are some problems in the homework where you're just given a compound, you have to say, okay, is it AQ or a solid? And then a little bit of nomenclature is mixed in there too, so it might give you like just the elements, and then you got to come up with the formula, and then you also got to then predict solid or aqueous. All right, so the problem I want to go ahead and do is a precipitation reaction. Oops, presenter camera, this one. All right, so here we have sodium acetate. Sorry, sodium carbonate is the one that I want to do with this one. And then we'll fill in our states here in a second. So I'm leaving myself a little bit of space to write the state in if I need to. And then we say plus, this is going to react with MgCl2, like so. And then leave myself a little bit of space. And just make sure we're all clear here. We are working on a precipitation reaction. And I like to write RXNS short for the word reactions. All right. Typically what happens with a precipitation reaction is they're generally a double displacement. That is the generic category they fall into. All right, like so. And then what we're going to do now is we're going to go ahead and do partner swaps here. So what I mean by that is magnesium goes to carbonate, sodium goes to chloride. So MgCO3, and just like we always have to do, we have to make sure the formula is actually right. If you need any subscripts, anything like that, we don't need those on this because we have a 2+ on magnesium, and then we have a 2- on carbonate. Hope you guys remember these polyatomics. They are going to come up during this chapter. All right, and then we have sodium chloride. Okay, so predicting solubility, I'm going to go ahead now, fill in all our states, and then we'll go ahead and balance it, and then go from there. So this one has sodium in it, automatically soluble. Sodium is one of the exceptions. That's always soluble. Same deal on the product side. The sodium compound is soluble. All right, and then we have our MgCl2. So I'm just going to go ahead and pull the table up again. All right. So we're seeing chlorides there. Chlorides are typically soluble. They have some exceptions. Magnesium is not amongst the list here, so that means that magnesium chloride is aqueous. So AQ. And then when we do the same thing again for the magnesium carbonate, I really wish I had a zoom on this camera. Kind of don't have it in frame. Well, that's about the best in frame that I'm going to get it. I'll think about that writing in the future. All right, so magnesium carbonate, going back to that one. So we take a look at the table. We typically look at carbonates, so carbonates are on this table. So we see carbonates at the bottom of the table on the insoluble table, and then we go ahead and see that magnesium is not one of the exceptions. That means this is insoluble. Magnesium carbonate is insoluble, so S for that one. I think I might pull up a view where I actually have, hang on, let me do this. I'll mess with it in a minute. All right, so at this point we now have our precipitation reaction written out. The reason why we call it a precipitation reaction is imagine you had a solution of this one, and you mix them together. What you would actually see is these would appear to look like water because they're soluble, and then the solution becomes kind of cloudy, opaque, meaning you see like a solid forming in solution. Typically, if things are perfectly clear and colorless, or clear meaning you see through the solution, typically that means they're aqueous, things are dissolved. And then if they appear to be opaque, you see like a solid in it, kind of floating around, that means insoluble. So this is actually our precipitate in this reaction, if you were to mix these two together. Precipitate. All right, you're solid there. All right, so let's go ahead and do some mass balance here. This is not balanced here, so we need to write our sodium, or make a list here. And just like we saw in one of the old last problems, we do have polyatomics that are not changing. We have carbonate to carbonate, not changing. I'm going to treat it as an element. So CO3 2- is one element, basically, in how we're going to work this out. And then we have an Mg and a Cl. Let's go ahead and, hang on, let me move this over. Wow! Anyway, we have 2, 1, 1, 2, and then on this side we have 1, and then we have 1 on the carbonate, we have 1 on the magnesium, and we have 1 on the chlorine. It's all 1, 1, 1, 1, 1. Alright, so starting off, I'm just going to go top to bottom. There is no set rule really. It's all what you find as you experience, what's easier, where to start. And the general rule that I gave you guys was, generally in my experience, if you start at the heaviest metal first and then leave any diatomics for last, generally that's okay. So here, I'm going to go ahead and drop a 2 in front of this one, and that'll give me 2 sodiums. It also makes my chlorides balanced too. We now have 2 chlorides balanced out. And then it looks like we're balanced. That's all we had to do. That was pretty straightforward, wasn't it? So we're all set. So let's see if they work out that easy on the test, right? They typically don't work out that easy. All right. So I want to go ahead and expand on this. So typically we have our balanced chemical reaction right here. We'll oftentimes take it a step further and break this apart. So we're going to be building up to what's called a net ionic equation. So let's go ahead and take a look at this ionic equations. So generally what we're going to be doing here, basically, we're going to be kind of cutting away or like trimming the fat from the reaction, and this allows us to kind of focus in on the reaction, on what actually is happening. It's like being able to see the, you can't see the forest for the trees kind of situation here, because there's too much detail. If you actually take out the things that aren't involved, it makes the reaction look a lot simpler. So what we do is you can break apart anything that's aqueous. So break apart AQ into ions. We're going to break them apart into ions. So what I mean by that is, here we have a couple aqueous species. So I'm going to rewrite this as 2Na+. So notice here I put a 2 in front because from the formula we have 2 sodiums. So that 2 ends up going in front if you're breaking things apart. And then we have our carbonate. No subscript there or no coefficient here because we only had 1 in the formula, so you don't have a coefficient here. And then we have the other compound we need to break apart, and that's also aqueous. So we get a Mg2+, and we have our chlorine, and then notice how the chlorine has a 2 subscript, so that gets pulled in front like that. And then for the sake of space, I'm going to just write underneath here, but this is actually one long reaction. You leave anything that is not aqueous alone. So anything that's solid, liquid, gas, just leave it alone. And I'm going to leave it together. So MgCO3, this was insoluble, so solid. And then I'm going to break apart the other one. So here we have our aqueous ones, and we have to tag these onto each individual ion also. So that way we maintain our mass balance when writing this out. So we have 2 sodium ions and 2 chloride ions. All right. When you have your equation in this form, you now have what's called the total ionic equation. So total or complete ionic equation, I've seen it written that way too, but I like to say total ionic equation like that. All right. The next thing we do after here, typically this is not the stopping point, so I'm just going to scroll up a little. We then take a look for the species that are identical on both sides, and we refer to them as a spectator ion. So I have a new definition for you guys. Spectator ion. These are ions that they have no change in the reaction. So no change during reaction, and they're exactly that because they didn't do anything. They're kind of just watching on the sideline. They're the guys sitting on the bench watching the action happen. So they're not doing anything. So you need to, what we're going to do here is we're going to identify the spectator ions and cross them out, and then we're going to kind of focus in on what actually is happening here. So here you want to cancel spectator ions. So then looking at the reaction here, sodium is going to be one of your spectators pretty much all the time, because remember, these are never soluble. So I have a sodium and a sodium. They cancel out, like so. And then, so look here, so carbonate, here we have aqueous carbonate, and then here we have as part of something. These are not the same. So we can't cancel those. They have changed. Same thing with magnesium. Magnesium here was by itself, and then here it's part of something. That is technically a change. You leave it alone. And then next species here, we have two CLs, they look the same, the way I wrote it out. They drop out also. You then want to rewrite the equation without the spectators. So rewrite reaction without spectators. So rewrite your reaction without the spectators, and the general convention on the way we do this is just how you do the formulas. So remember, when we're doing formulas, we typically go cation then anion. You kind of want to do that also in these reactions here. So I'm going to shuffle it around a little bit. I'm going to put magnesium first because that's your cation, Mg2+, and then excuse me, we have a carbonate, and then these are becoming magnesium carbonate solid. And remember earlier in today's lecture that I mentioned that when I write them like this without the AQ, it's kind of implied. Just for the sake of the notes here, I just want to go ahead and include them so you guys are all crystal clear on what's happening. So two things that are dissolved, they're ions that are kind of floating in solution, they come into contact, boom, they crash out, they become this. All right, let me check the Discord. Few people in here still, so I think I'm actually getting views right now. Weird. All right, so I would, at this point, I would ask if there are any questions, but you guys have any questions? Anybody have a mic on Discord want to see if this works or not? I would love it if you guys would actually ask a question. I want to see if this actually works or not. Nobody? Bueller? I'll show my age now with that. All right, I guess what we can do, I'll just go ahead and do another one, and we'll go from there. All right, so let me go ahead and just start a new one. I think we'll do one more, and then we'll do acid base, and then I wanted to wrap up the chapter today, but you guys are definitely have to do a lot of homework in this chapter. You got to practice these reactions and work with the balancing, all that fun stuff. All right, so let's go ahead and do another precipitation problem, and then we're going to go, starting out, we have these two compounds, putting them together, getting a reaction, balancing it out, and then breaking it apart into, the complete ionic equation, and then we're going to go ahead and do the net ionic equation and see how it turns out. So we have, I'm going to go ahead and say we start with iron nitrate, and iron 3 nitrate. So I'm going to go ahead and put 3 nitrates on here. Remember, for your transition metal, you kind of have to specify. Iron can technically be a +2 or a +3, so you got to kind of specify the name. Let me just write this down here just for funsies. So this is iron 3 nitrate, and then suppose this is someone was reacting this with, say, potassium hydroxide, KOH. This is right up here, search the room. Potassium hydroxide. Just practicing our naming. I did test you guys on it, but it's going to show up again anyway. All right, so remember, precipitation reactions, they partner swap, and then typically it's going to work out in these also where both things on the reactant side are soluble. So if you have your table handy, you may see that nitrates are always soluble. There are no exceptions to that. So AQ. And then here, hydroxides are typically insoluble. We have one of the ones that is always soluble. So, and that's consistent between the tables. So KOH is also soluble, AQ. And then we need to partner swap them and then make sure that we're keeping into account our charges. So I like to, for things that remember, that's shown as a 3+ there, 1-. You don't have to do this step, just you want to think this kind of stuff when you're writing things out. All right. So iron is going to go to hydroxide. So FeOH, like so. Iron hydroxide, specifically iron 3 hydroxide, and since hydroxide is a -1, we got a +3. You need 3 of these ones. Leave yourself some space for the state. It may be aqueous, maybe solid. We'll do that after. And then we take a look at the other ones here. Potassium goes to nitrate. So here we have KNO3. Potassium nitrate. Notice here these both are definitely the ones that are on the always soluble chart. So this is definitely AQ, like so. Both other ions are always soluble, so for sure, don't even think about it. If you memorize that part where the ones that are always soluble, no exceptions, you're off to a good start. Alright, so hydroxides, those ones were actually ones that are typically insoluble, but you got to check the chart if you don't have it memorized. And then here, hydroxide, I'm seeing here that iron is not one of the exceptions, so this is definitely insoluble. Alright, solid. So I actually do this reaction, if we were doing this in class today, actual class, I actually would have brought these chemicals and I probably would have used sodium hydroxide instead of potassium hydroxide. But the reaction would have been the same, except for it would have been an Na instead of K. But when we actually do this reaction here, this reaction ends up being like a black gelatinous solid. This part tells you nothing about that. You actually got to see the stuff in the lab to kind of see the colors. They're not all white powder, but yeah, this one was like a blackish, like gelatin when I made it. But it's technically insoluble. It's, it's gelatin kind of looking, but it's definitely both insoluble. All right, we then need to go ahead and balance this here. So make tally up. I just read it left to right. So it's iron. We have a nitrate, which is not changing, so that's treated like an element. And then we have a potassium, and then we have hydroxide. Just like before, we got a hydroxide here. It's not changing. It's a polyatomic. We just leave it alone. All right, we got 1, 3, 1, 1 on this side, and then this side we have 1, 1, 1, 3. So I'm just going to go ahead and start off balancing the one that maybe the hydroxide. You can do nitrates first, and kind of whatever to start somewhere. We can't start with iron because iron's already balanced, so we got to start somewhere else. So I'm going to start with nitrate, see how it works out. So nitrate, I can balance nitrate by putting a 3 on this side. So 3 potassium nitrates, we now have 3 of those guys. And then what else did we change? We changed potassiums over here. We got 3 of those. All right, excuse me. And then looks like on this side, if I just drop a 3 in front of KOH, we're done. Boom, boom, 3, 3, 1, 1, 3 all the way down. We're good. All set. We're done with the first part. Depending on what the question is asking, sometimes they actually stop here. And then a lot of other ones are going to say net ionic, so that's what they want. All right, so let's go ahead and do the net ionic. It's going to do another sheet of paper here, just so I can kind of stack this stuff together. Okay, so you stopped drawing it so wide. I'm really sorry. Just drawing it the way I would in class. So remember, you can break apart anything aqueous, anything solid, liquid, gas. You got to leave it alone. So I'm going to break up this one, leave this one alone, and then break up that one. And you got to keep in mind we have coefficients and subscripts we got to keep in mind when we're doing this stuff. So this first one is going to be an Fe3 plus. The nitrate here has a 3 in the subscript, so you need to make sure you include that here. These are all aqueous. Remember, they're all aqueous when they're ions that are separated out. All right, so that part's done. And then here we have 3 of this whole thing. And then breaking this apart, we get a K plus and an OH. Remember, we had 3 of them, right? So 3, 3. And then I like to do this in 2 lines because it ends up being super wide when you write it out. So I just go ahead and just do a second line underneath. It's going to work for the camera view too. So we will solid alone. And then I like to include that there too, just to make sure I'm like keeping myself straight in my head which one is the solid. And then break apart the other one. So 3K plus, remember this, we have 3 of these guys here, so 3NO3. Okay, so then we analyze, so we now have the complete ionic or total ionic equation. We then need to go through and cancel things that are the same on both sides. Basically cancel the ones that are not part of the precipitate. It's typically how it works out. So potassium, they drop out. K plus, and then what else? We have nitrates. So nitrate, they have the same number of them as well. That's also a thing. You're going to have the same number of them as well. If you don't have the same number of them, they do not cancel, but we don't actually see problems like that in this class. That's a 121 thing. You see that with, I'm thinking Hess's law, but yeah, way ahead of myself here. All right, so let's go ahead and take a look at what's left. So we have iron 3 plus, we have hydroxide, and then you go ahead and rewrite it. Put in the cation first. Remember this, the cation goes first, and then we're going to have 3 hydroxides, like that. And then if you want to just, if you want to tack it in, just wait till the end. That's fine too. On a handwritten test for me, I'm actually fine if you leave them out, but I do make sure that you guys include the solid one at least, because it can be very time consuming to write these out on the test situation. All right, there we go. There's the whole thing written out. Little pro tip, little thing that I've observed over the years of teaching this class. I've noticed that typically how this work is you'll have a situation where you have one soluble, one insoluble on the product side. If that is the case, typically the one that is soluble are spectators. So these ones here, so AQ on product side, they are typically spectators. So I'll put spec for short there, but they're typically the spectators. All right. So I want to go and do one more example before I move on to the. I definitely want to do acid-base today, and I think I'm actually going to end with acid-base today, and we'll pick up from there next time. So let's go ahead and do one more of these guys. We have some weird situations sometimes coming up with these. So let's go ahead and see one of these examples. So what if we take something like, let's say, let's work with nacho again. I can't help but see, you guys aren't going to unsee it either. I see this totally with nacho. But sodium acetate, nacho, always soluble. And then let's suppose we're doing a reaction with, say, KCl, potassium chloride. This is also aqueous. Notice how we have these soluble ions in them. And then let's go ahead and do the partner swap thing here. So sodium goes to chloride, potassium goes to acetate. And so I just want to be clear you guys are thinking about this. Like, imagine you have these two things, when they go into water, they're breaking apart, and they all kind of get intermixed together. And the ones that are going to precipitate out, will eventually find each other, and they fall out of solution together. So these are all four floating around in solution. They swap partners. So then we end up with KC2H3O2. And let's go ahead and do solubility as we go around. So go along. So notice these are both soluble. What's going on here? And then sodium goes to chloride, NaCl, AQ. All right, so we have a situation here where if you think about it, so now at this point we would typically break everything apart. I also want to point out it's already balanced. They're all 1, 1, 1, 1 across the board. But at this point you think about, okay, we're going to break things apart. If you broke everything apart and then canceled it, everything cancels. So let's just do that for the sake of discussion. So Na plus, C2H3O2 minus, K plus, Cl minus for the reactant side, and then we have K plus, C2H3O2 minus for the potassium acetate, and then we have our Na plus Cl minus. There's no solvent species in here, so there's actually no difference between any of these ions. These really all cancel out. So in that case, this case, no reaction actually occurred here. So no reaction occurred. So no reaction occurred here. So typically what you do here is you would actually write just NR here. So NR stands for no reaction. So this is no reaction occurred. And yes, this could pop up on the exam. You know how I like to be tricky, I guess, right? You guys say so anyway. So yeah, if you have a situation where everything's soluble, no reaction occurred, just write NR in caps. It's typically what people do. All right, let's go ahead and take a look at an acid-base reaction. So I did want to use PowerPoint a little bit for this part, just to kind of give the introduction on what acids and bases are. So switch over here. I believe I have this tagged as slide number 87, if you're following along with the PowerPoint with me at home. Oops, this is a different one. Hang on. Nope, that was for a different slide. It's actually a little bit earlier here. Actually, let's just go ahead and start here. So, properties of acids. All right. So, yeah, properties of acids. These are just talking about their kind of physical properties here. Typically, they do have a sour taste to them. If you were to get them in your mouth, some common things like like your lemon juice, that's citric acid. It definitely has a sour taste in your mouth. That's a very common thing here. They can change the color of vegetable dyes. One common demo we do with this here is we actually take red cabbage and actually, grind it up in a blender, get the juice out of it, and then it actually changes color with acids and bases. It's pretty cool. It's like a natural pH indicator. I would have did that in class too if we were in class. Oh, bummer. So, anyway, it turns out that acids do react with active metals. Don't worry now about what is an active metal, what isn't. It's a whole thing with activity series that we teach next semester. But for now, if I show a reaction with acid, we're just going to go ahead and assume it happens. But there is a way to predict if it actually happens or not, how it happens, or if it happens, and that's called activity series next semester. So they do often react with things like carbonates, producing CO2. We're going to cover that reaction definitely before we end class today. All right. Hang on, next slide. These are some common acids. I think I'm not going to have you guys worried about memorizing these. There is ways to there are different strong and weak acids, and typically we go over like memorizing the strong acids. I'm not going to worry about it in this class, but for sure in 121 you're memorizing those strong acids and how to recognize them. But the general thing I want to talk about here is that remember when we did the acid naming during the nomenclature chapter, typically we have the H first in the formula, and that's going to serve as the cation for that side. And these acids, if you think about it, H is the group 1. These are always soluble in solution. So these acids are always going to have AQ on them if you're putting them in a problem. The more trickier part for people might be like recognizing what a base is. So a base is something that reacts with an acid in a so-called acid-base reaction. You're going to see that they're very similar to precipitation reactions. They're kind of a specific type of a double displacement. So some properties of bases. Keep in mind that the word basicity and alkalinity kind of mean the same thing. At least in this class, we're going to mean the same thing. The most common bases we're going to see in this class are things like hydroxides, carbonates, sulfides, ammonia. Those are we only have a handful of bases that you're going to have to remember, and I'm going to kind of show them all the different ones that we're going to see in a few practice problems. So don't worry about that. We also got a slide here for the common bases. So you may know. There we go. You may notice here that all these compounds are hydroxides. They're going to react with an H+ in an acid-base reaction. So let's just go ahead and do one. Yeah, just go ahead and do it. So we'll take an acid compound, a base compound. We do a double displacement reaction the exact same way that we did during the precipitation reactions, and it's going to be very, very similar. You'll see. This is just another type of reaction. And I think we did one actually in the class last time, but let's just go ahead and take a look. So let's go ahead and say, let's do like the mainstay that everybody does is their first reaction here for acid base, HCl. This is going to be aqueous. Acids are typically aqueous, so AQ. All the acids in this class are going to be AQ. It's typically the organic ones that end up being, insoluble, but yeah, that's 3 semesters away from now. So yeah, all the ones in this class are AQ. And then let's suppose we reacted with NaOH, sodium hydroxide, definitely a base. It's a hydroxide base, and it's got sodium in it. It's water soluble, AQ. All right. So what's going to happen here now is they're going to do a partner swap. So H is going to go to OH, and then Na is going to go to Cl. So if you think about it, we're going to have an H and an OH. That's just water. So H2O. It doesn't make sense to say you have aqueous water. It's like, so typically what we'll do for water in a product, you don't say it's aqueous, you say it's liquid. So L. This is going to allow us to keep water when we do we cancel things out for Ionic equations. Water is going to end up staying because it is not aqueous here. It's L for liquid. Then what are we going to have here? We're going to have Na and Cl. AQ, like so. All right, so now we have all this out here. We can go ahead and check for mass balance. This one actually worked out to be already balanced. We can actually do it by atoms here. So HH, there's two H's, oxygens, one oxygen, and then sodium, 1, 1, chlorine, 1, 1. We're done with balancing anyway. So we're going to go ahead and treat it like we did the last ones. We're going to go ahead and break it apart and split things up. But I forgot to write this out. The compound with H in front is your acid. The compound with the OH in it, that is your base. All right, so breaking things apart here, we're going to go ahead and break apart the aqueous. HCl to be H plus and Cl minus. And then we're going to go ahead and break apart the NaOH, sodium hydroxide, to be Na plus and hydroxide, OH minus. And just like before, I'm dropping the AQs here just for the sake of space and making the drawing clean here. But technically, AQs are on each one of these. When you're doing the online homework, though, you guys know how mastering is now. It's super picky. It wants that AQ on everybody. It'll mark you wrong. I won't, though, in lecture. All right. So water stays. It's not aqueous. We leave it together, and then we go and learn. Or sorry, go ahead and break apart the Na plus, Cl minus. All right. Typically, the way these ionics are going to work out, especially with hydroxides, is you're going to have your acid, which is H plus, your base, which is OH minus, and then they combine to make water. So what I mean by that here is sodium cancels out, chlorines cancel out, and we literally have H plus OH minus gives water. So H plus, OH minus yields H2O liquid. So pro tip here, if you are working with an acid-base reaction that has hydroxide for the base, this is always the Ionic equation. I have not seen an exception to that. And that's only true, once again here, if your base is hydroxide. So net ionic for acid plus hydroxide base. These are super common. You're gonna see these all over the homework. So you guys got a leg up. You see a reaction, boom. You already know what the ionic is. It's gonna be that. You should practice working them out though to make sure that you're confirming that you're getting that, because sometimes you have some mass balance issues that show up in the complete ionic equation. All right, let's go ahead and do another one here. One where it's not 1-to-1, and we'll see how that works out. So let's go ahead and say that we have, let's say, sulfuric acid. Sulfuric acid is H2SO4. This is going to be aqueous. And then suppose I want to change the base this time. So let's go ahead and say it's a sulfide and potassium sulfide. So be thankful that I'm not bringing this stuff to the lab. It turns out, or sorry, to the classroom, because sulfides smell like rotten eggs. Yeah, so I wouldn't bring this to the classroom anyway. It smells pretty foul. All right. So if you're confused, I mean, you can just remember what things are, but I just want to make sure that everybody's understanding what an acid is. It's the one that typically has the H in front in the formula, but more specifically, we're going to say an acid donates H plus, and a base accepts H plus. It turns out that we'll go to it more detail in Chemistry 121, but in this class we're going to use this definition. It turns out there are technically 3 definitions for an acid, what an acid and a base is. They kind of end up overlapping a little bit, but just for the sake of a completion here, this is the Bronsted definition. This is the one that we're going to follow in this class. So there's also the Arrhenius definition, which focuses on H's and OH's, and then we have the Lewis definition, which focuses on electrons. But in this class, and most classes honestly, Bronsted is the definition that we go by. So if you think about it by this format here, the H is going to go to sulfide. So this one's accepting the hydrogens. That's your base. In the last reaction, that was hydroxide, but here it's sulfide doing it. The one giving the H's is your acid. All right, partner swapping now. So we're going to go ahead and say that we're going to put potassium. I think we're going to be 1-to-1 like the last one. Oh well, whatever. But we'll see. So what do we have here? We have K2SO4, AQ, and then we're going to have H2S for this one. So for the last example, we actually saw that for like the equivalent would have been water. It turns out though that H2S is actually a gas, and we're going to go over acid-base reactions to cover gases next time. We don't have time today, but it turns out this one's actually a gas, and if you look ahead, you'll see why there are certain bases that make gases when they get reacted with. All right. I think I showed the poor example here. They're all 1-to-1 here in the balancing here. We are going to go ahead and break it apart though and see how things work out. So I'm going to go ahead and use another sheet of paper for this. I'm going to burn so much paper doing this. This would have been on the whiteboard in the classroom. So. All right. There we go. Remember, break apart anything aqueous, anything solid, liquid, gas, leave it alone. So we're going to get 2H plus sulfate, and then 2K plus S2 minus for the reactant side. And then on the product side, and we're going to see just like we saw the precipitation reactions, the one that's soluble on this side typically is spectators. It's gonna work out that way for this one. Most of them, it's gonna work out that way. All right, so here we go ahead and see H plus. So typically the compounds that are your acid base aren't going to cancel. So these aren't going to cancel, but these ones are. So we're going to see sulfate, same, and then K plus, potassiums plus, they cancel out. So then rewrite the whole thing. Make sure you put the cations first. That's the standard convention. So the cation here is the H plus proton, or acid hydronium ion. And then we have our S2 minus. And then H2S. All right. So there is our net ionic equation. We are done with this problem at this point. So you definitely want to practice these reactions, guys. I did want to I did have a meme for the day, but I actually had the meme for the end. So hang on, let me switch over to different view. All right. Oops. Let me silence that. Oop. Hang on. I got it. All right, and let me make this smaller. You're actually seeing my streaming software now. Using XSplit for the software. But there is your meme for the day. If you can get this small enough, I can hide it. That's as small as it gets. Anyway, there we go. Brace yourself. Stoichiometry is coming. I believe that stoichiometry is easily the hardest topic in this course. The thing about stoichiometry is not only do you have like all the stuff that we're doing. What am I doing here? Hang on. So all the stuff that we just did, but you also have to consider like how much mass you're starting with, how much mass you get out at the end. So that's actually next chapter. For this chapter, we need to get solid on the chemical reactions. So let me just bring this back here. God, I'm still fumbling with this stuff. Hopefully it's better next week. But I'll have had a few lectures before we do it the next time. All right. So I'm gonna go ahead and end the class here, guys. Hopefully you guys got something out of this. I'm actually asking those that watch this to please give me feedback, because this is literally my first time doing this kind of thing. So please give me feedback on what you guys think on how I did, and if you want me to fix some things, whatever, please just give me feedback. I really want to know how this is working out. I have no idea how it's seeming from your perspective. So yep, let's go ahead and end the class. Oh, look, 1 minute left to go. It's 10:49. Let's go early today. All right, I'll see you guys on Monday. Remember, I'm actually just gonna leave my Discord open. So I'm technically in office hours right now. I'm kind of just running around my house, probably gonna have lunch. But yeah, I'll leave my Discord open. You guys just drop in, say hey, Professor James, blah blah blah. Ask questions. Anyway, guys, please be safe out there. The governor did close down everything. Do not go outside unless you absolutely have to. So if you're running, don't go run to the store. I think grocery store is probably the worst possible place to go right now. I bet there's probably like 1,000 people at the Albertsons down the street from me right now. Do not go outside your home, guys. I saw a phrase that they were saying it was like "stay home for Nevada." I'm believing that 100%, guys. Stay home for Nevada. We need to be healthy here. I don't want to hear about deaths in Nevada, at least more than we've already had. So yeah, guys, be safe. I'll see you guys on Monday. And Discord. All right.